Hello, now I'm going to go through another large-scale example, in this case, a complete central processing unit or CPU. One key thing I'm going to show you in this example are the value of identifying micro-operations as an intermediate point in doing your design. Teaching design is difficult because it, to some extent, is teaching creativity. All I can do, I can't make you more creative, but all I can do is put tools in your quiver that help you identify how to structure a design from a high-level intent or a high-level algorithm. In this case, the high-level intent or the high-level algorithm are how to execute instructions in a simple processor. This example is taken from this reference given here in Patterson and Hennessy. So what we're going to do is design a CPU from the top down to the data path and finite state machine controller. I'm then going to show you how to the Verilog RTL that corresponds to this, and finally going to outline a pipeline version to introduce the concept of pipeline controllers, which we did refer to in the complexity notes. So what we're going to do is start off with a simple specification and then go through the design steps in order to obtain a processor. Again, a key thing here is designing the data path first. In order to do that, the key step that we're going to take is to identify what sequence of micro operations are required in order to execute the required instructions. Then we're going to work out a good sequence for those micro operations that maximizes the performance, and actually in this case the performance per unit area of the data path. After doing that and designing the controller, which is a finite state machine, I'm going to illustrate the design and operation, show how to add exceptions, then get to the coding. So this is the specification. It's a simple MIPS processor. We are only going to support a handful of instructions in order to keep this relatively straightforward. We're going to have ALU instructions, which operate on registers, add, subtract, and an OR. We're going to have memory reference instructions that fetch and store data from registers to memory, load word and store word. We're going to have control flow instructions, branch on equals, and jump no matter what. Towards the end of this section, I'm going to illustrate two exceptions added to this undefined instruction and overflow. And overall, I'm going to stick to a performance objective here. That is, I want to minimize the time it takes to perform each of these instructions, actually all the instructions on average. And that is the sum, that is the multiplicand of the clock period times the number of clock cycles it takes to perform the instruction. And actually what you'll see are there simple things we can do to the data path that greatly improve this figure of merit. Again, I remind you, this is a complex design. This is the most complex design that I'll go through in these lectures. And again, one key step in order to manage the complexity is to postpone dealing with the controller. I'm going to start with the data path. The controller essentially falls out of the data path design, though with a lot of engineering effort, I will admit. So we're going to start with the data path first. When we get to the controller, what we'll do is we'll identify status lines coming from the processor and the control lines going to the processor. Many of these are select lines on multiplexers. So what we're going to start off with is to rough out the design. That is, identify the major elements that have to be in the data path. Then we're going to determine in detail what are the micro operation sequences required to perform the required steps in the specification. In this case, the specification is to execute other types, specific types of instructions. But in general, in any hardware design, you can go from the algorithmic intent to a set of steps that have to happen in the hardware. These steps are best fleshed out as micro operations. Key in a microoperation is it specifies a register-to-register transfer without getting into formal language. And then we'll go on to the detailed control flow in the next submodule. Okay, so let's start off with the major data path elements to make a functional CPU. What we're doing here is roughing out the design. What are the big blocks that are fairly obvious to us that are useful to us? Well, let's think about this. We have to do arithmetic operations, so we'll need an ALU. We have to work with registers, so we'll need a register file to store these. We have to work with a memory because we're doing load word and stored word to and from the memory. We have to keep track of where we are in the execution of the instructions. So we need a program counter, and we have to have somewhere to install the instructions. That is an instruction register. And often it is the case, and certainly is true in this design, that the memory has registers going to it on the address line, in this case the program counter, and going from it on the data line, in this case the instruction register. But as well as fetching instructions from this memory, we have to fetch data. And so we're also going to add a memory data register, and in fact we'll add later a memory address register up here. So here we just roughed out the design. It doesn't have to be perfect, but we've got the major elements at least started in order to iterate towards a good data path design. So the next step is to take our algorithmic intent, in this case the specifications of the instructions, and work out in detail what has to happen on a data path, which will eventually be a modified version on the previous page. We'll work out what has to happen on the data path in order to execute these instructions. And again, though here I'm dealing with an instruction set processor, these steps can be applied to any design. We actually did this in the motion estimator. There was only really one type of microoperation that mattered. So it was relatively simple. Here we've got the inverse situation. We're going to have lots of microoperations leading to a more complex, more convoluted data path. But this is a key step. If you can do this step, you're well on your way to having a good design that meets your algorithmic intent. So let's start with add. This instruction format on the right, what we're doing here is adding the register RS to the register RT, storing the results in register RD. All of these are addresses in the register file. They're stored as 5-bit addresses here. It's a 32-entry register file. The opcode for ALU instructions is 0. We need this func field to identify which ALU instruction, add, subtract, or AND. And in this case, that func field will specify an add. Let's go through the microoperation sequence that has to be performed, has to be carried out in the hardware to execute this instruction. Well, the first two are common to all instructions. The first step in fetching an instruction is to fetch the instruction. Is the first step in executing instructions to fetch it from memory. It is in memory. We need it in the data path because we need to pull things like these register addresses from that instruction. So what we're going to do is we're going to reference the memory with the address stored in the program counter. What is stored in the memory, that address, will be stored in the instruction register. Here I'm writing a micro operation that captures that operation. This is not meant to be code. This is pseudocode. It is high-level code that is specifying one step, one of the required steps in executing an ALU instruction. In fact, all instructions in this case. Notice it is operating from register to register. It is, in a sense, RTL pseudocode. The other thing we have to do for each and every instruction is increment the program counter. So we might as well get that out the way early. PC equals PC plus 4. Each instruction here is 4 bytes long. So and this is a byte addressable memory, so we increase the program counter by 4. The next thing we have to do is actually perform the execution stage of this instruction. Again, what we're doing is looking up in the register file with address RT, looking up in the register file with address RS, taking those results in the register file, applying whatever the function to it is. Remember, we also have subtract and 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 OR as well. I'm just illustrating this with add. And store the result in the register file at address RD. We have now completed a micro-operation sequence for this instruction. Let's look at the next instruction in our set, load word. What this does is forms an address from memory from the contents of register RS added to this 16-bit offset, which will need to be sign extended. Look up in memory what's happening at that, what's stored at that address, the 32-bit word that's stored at that address, and store the result in RT, which again is a register in our register file. What are the first two micro operations in the execution of this instruction? You've guessed it. Fetch the instruction, store the result in the instruction register, and increment the program counter by 4 bytes. What's the next step we have to do? Well, think about what are the steps we have to do here. We have to calculate the address. We have to fetch what's stored in memory from that address and store that result in RT. Let's capture that as a reasonable set of micro operations. First, I'm going to calculate the address and store this in the memory address register. What I'm going to do here, it's correct. Oh, sorry, I'm jumping ahead of myself. I later inserted a memory address register. This is the entire micro operation written out as one step. I'm going to take what's stored in the register file at register RS, add the offset to it, sign extending it into a 32-bit word. That becomes the address in the memory, and I'm going to store that in the memory data register. Later I'll calculate. This takes too long, so I'm going to break it up by having some immediate steps. But this is my initial roughing out of the micro operations required to complete this, to execute the load word instruction. Then I'm going to take what's stored in the memory data register, which is coming out of the data port of the memory, and store that in the register file at address RT. So here is a plausible set of micro operations. We'll fine tune these later. A plausible set of micro operations that, when put together in this sequence, execute the algorithmic intent required for the load word instruction. I'm not going to show store word. It is similar, except the reverse, obviously. We're storing a word in memory rather than retrieving a word from memory. Let's look now at jump. The format of the instructions, the opcode for jump is stored in the first 6 bits. That's the opcode for that is 2. And we have a target address, which you'll notice is not 32 bits long. So we'll need to we'll need to extend it. Actually, what I'm going to do is pad it with the current concept of the PC to get to 32 bits and do something else, which you'll see in a moment. So what I'm doing is jumping to a target address. Again, the first 2 steps of performing any instruction is to fetch. The first step required to perform any instruction is to fetch the instruction register. Obviously, to perform this instruction, we don't need to increment the PC. We're going to actually do the jump by changing the contents of the program counter. So the micro operation required to actually complete the execution of the instruction is to take this target address, concatenate 2 0 bits to the low order 2 bits of this target address, and concatenate it with the high order bits of the program counter so as to get a 32-bit address. The reason why the bottom 2 bits are 0 is because all instructions are 4 bytes long. Thus, the first 2 bits of an address for any instruction, the low order bits have to be 0, 0. These are the required micro operations to perform a jump. Let's now look on branch on equals. What we're going to do here is compare RS and RT by subtracting them and looking at the 0 flag coming out of the ALU. If they are equal, we're going to replace the PC with the current PC plus the offset sign extended. So first step is to fetch the first micro operation is to fetch the instruction stored in the instruction register. We still do PC equals PC plus 4 because we don't know if we're going to modify the PC or not. We then fetch contents of the 2 registers from the register file, subtract them from each other, and dump the result. We don't actually care about the result. What we care about is whether the 0 flag is set or not. If the 0 flag is set, we're going to modify the PC by the current PC plus the sign extended offset. Again, shifted left 2 because all instructions are 32-bit aligned. And of course, what happens is when we get to the next instruction, this is now the new PC. So the next instruction, which of course, whatever it is, always starts with this micro operation, will start at that new address. So now we have a plausible set, they're going to change, but a plausible set of a sequence of micro operations that take the algorithmic intent, in this case instruction execution, and break them down into register to register micro operations on our data path. Next, what we're going to do is try to work out the sequence of these register to register operations. And we're going to play with this a little bit, together playing with the data path, in order to try to minimize the sum of the cycles per instruction times the clock period. And in doing this, we are actually going to add additional data path elements for reasons you'll see in a moment. This then defines the control sequence of the controller hardware, which we'll get to in the next submodule. So this is our first attempt at a hardware design. All right. Now remember, what happens on the first clock cycle is we fetch the instruction. So we don't know what the instruction is until the start of the next clock cycle. So none of these steps down here can be put into the first clock cycle. Here I've got an approximate timing for my data path. I'm assuming the memory takes 10 nanoseconds, reading or writing the register file each take 8 nanoseconds, and an ALU operation takes 10 nanoseconds. So what we're going to try to do is work out the minimal number of clock cycles to execute the required micro operation sequences on this data path. For each instruction, we're going to do the instruction fetch and the PC increment on the first clock cycle. And in fact, for jump, we're going to have to actually later do the PC increment because we don't know yet that this is actually a jump. We don't know what the instruction is until it's stored in the instruction register at the beginning, by the beginning of the next clock cycle. In the second clock cycle, for the ALU, we do the entire execution stage. That is, read the register file, go through the ALU, right back to the register file. For the load word, we're going to write to the memory data register from the address that's calculated by reading the register file, adding that, and fetching the memory. Then the third clock cycle, because it's not complete yet, we're going to have to store that in the register file. The jump, we'll do calculate the new PC in the second clock cycle. For the branch, we'll have to take 2 clock cycles to complete this because both of these require the ALU. We spend 1 clock cycle doing the subtraction, and the third clock cycle changing the PC if we need to change the PC. So what we've done is try to move the micro operations up as early as possible, and for the different algorithmic steps that overlap, work out potential overlap of the micro operations. Well, let's try this out and see how we're at performance per unit area. At total performance. So the clock frequency works out to be 35 megahertz, as the clock frequency is 28 nanoseconds. The critical path is that set by this micro operation. But we have to do an add and a register reference and a memory reference. Together here, that takes 28 nanoseconds. And in fact, this is so much longer than all the other micro operations. We're actually going to show in a moment that we're going to add additional pipeline registers to this design in order to speed things up. Let's calculate the cycles per instruction times T clock for each instruction. ALU takes 2 clock cycles, load word takes 3 clock cycles, jump takes 2, branch takes 3. Clock cycle is fixed by the critical path at 28 nanoseconds. If all the instructions are equally likely, let's now calculate the average CPI times T clock. That works out to 70 nanoseconds. So the question is, can we do better here? And the realization here is that we have some pretty long sequences of calculations here, while at the same time we also have some sequences that are pretty short. And going back to this design, this is only a memory lookup. This is only an add. If we can break up these complex steps in the middle into shorter micro operations that are faster to execute, we might get a better total performance. So that's what we're going to try to do next. So this is that attempt to do that. What I am going to do is add I'm going to essentially pipeline the ALU. I'm going to put registers at the input of the ALU. So we spend 1 clock cycle fetching the registers, then 1 clock cycle performing the ALU operation, then 1 clock cycle doing the memory operation. Because you can see here I've got 10 nanoseconds here, 8 nanoseconds here, 10 nanoseconds here. We can much greatly speed up the clock period by putting these registers before and after the ALU. And as I said, I'm going to add another register to the output of the ALU, which is called ALU out. So when we are adding registers to shorten the critical path. That is really the best way to think about this. We're adding registers to shorten the critical path by breaking up the critical path into a 3 clock cycle critical path. This, of course, means we're going to take more clock cycles to complete our operations. On the first clock cycle, we're going to fetch the instruction and increment the program counter. On the next clock cycle, all we can do for the ALU and load word instructions, in fact, we'll just do this for all the instructions, so we don't have to know what the instruction actually is at this point, is just fetch whatever RS is pointing to and RT is pointing to into the registers A and B. And then the question is, can we do something else in this clock cycle since the ALU is not being used? And this is that answer. We're going to calculate the potential branch address earlier than we did in the previous execution stage. This was actually otherwise going to be empty. We're going to take 4 clock cycles to change a branch. Again, going back to here, we actually calculated the branch address last. Well, since we now have a clock cycle, since we now have a clock cycle in which the ALU wasn't otherwise being used, if this is all we did, well, let's use the idle ALU to calculate the branch address. We then do our ALU operation, our address calculation for load word, our address calculation for jump by changing PC, and work out if we need to do the branch or not. So here again, if the 0 flag is set from subtracting A minus B, because they're now presented to the ALU, then PC will be equal to ALU out, where we're temporarily storing the branch address. We've now finished the jump and branch equals instructions, but we haven't finished the ALU and load word instructions. The ALU takes one more clock cycle to write the result to the register file from ALU out. The load word takes 2 clock cycles. One to look up in memory and store it in memory data register, and another one to store the memory data register to the register file. Let's see if this has improved the performance of the design. What we've done is we've hopefully made the critical path a lot shorter. Unfortunately, we've on average extended the number of clock cycles required to perform our operations. So this may or may not turn out to be better, but let's see if it is better. So let's work out the clock period. It is now 12 nanoseconds. Or works out to 83 megahertz. That is, for example, reading this register, which takes 1 nanosecond, doing the ALU operation, writing to this register, which also takes 1 nanosecond. The path through the memory takes the same time, which, by the way, is one reason we're going to end up putting registers either side of the memory, on the address port and the data port. Let's then look at the CPI times T clock. The cycles are now longer. 4 cycles for an ALU, 5 cycles for a load word, 3 still for a jump and branch equals, or 3 for a jump and branch equals. And we multiply that by 12 nanoseconds, and we get this is the total nanoseconds required to perform each type of instruction. Let's now look at the average of those. 45 nanoseconds. We had 70 nanoseconds before. This is quite a bit faster. It's worked out that making the critical path faster at the expense of adding cycles has worked out in our favor because we made the critical path much, much faster. It's more than twice as fast than it was before. Now, of course, it depends on your design whether this works out in your favor or not in general. But in this particular case, it's made the design much faster. At a very small additional area overhead, we've only added 3 registers to the design. So the area per unit performance is also much better than it was in the previous version of the sequence of operations. Again, the key here is we took a complex micro-operation that was very slow, broke it into much faster micro-operations by adding registers, and then calculated our performance to see if it was going to be better. And again, this is the type of thing you can do in any hardware design to explore the different options to implementing your algorithmic intent on alternative possible data paths. Finally, to finish the data path, we have to actually make sure we have all the features required to perform all the micro operations that we ended up with. So we're going to now go through that and see if we have all those features, adding features if we need to. So this is kind of our baseline data path that we have so far, the major elements that we had, the ALU, the register file, the memory, program counter, the instruction register, adding in A and B and ALU out. So this is our starting point. We need a controller for the ALU, and that's just a given actually. So this also allows us to execute these micro operations. Let's do a complete list of the micro operations group by group and add features as needed in order to support them. Next one is the instruction fetch and the program counter increment. To do that, we need to take PC plus 4 from the output of the ALU, not from ALU out, from the output of the ALU. Goes into a mux here because there's going to be other things that are going to write to the program counter in order to perform jump and branch. And sending the program counter as an address to the memory on the address port allows us to read from the address port, go from the data port to the instruction register. The ALU out operations. ALU out's PC plus offset. This is for load word. For ALU operations. And A plus offset. This is for load word. I'm sorry. PC plus offset is for branch. Well, to do this, we have to add alternative inputs to the ALU. So these muxes here, as well as having PC and A and B, which we already had, we added in the part of the instruction register that stores the offset. And we also needed 4 in order to increment the program counter. So we're going to have these muxes going into the ALU. A and B are not the only choices that go into the ALU. Okay, then we have the micro operations MDR is equal to mem ALU out. If A equals B, then PC changes, and for a jump, PC changes. So we need to send ALU out to the PC in order to perform this micro operation. We need to take a modified version of the PC and feed that back to itself to perform this micro operation for the jump. We need to send ALU out as an address to the memory to perform this micro operation. And we need to be able to take the target, which is in the instruction register, concatenate with part of the PC in order to perform this operation. Next, write to the register file from ALU out and MDR with these addresses. These addresses, by the way, come from the instruction register. This is the address ports for the register file. The write port for the memory, we have to put a mux on it. We write from MDR. We also write from ALU out to the write port to the memory. So these are the read ports. This determines the addressing, and this is the write port. Finally, we haven't been talking about this much, but for store word, we actually need one more micro op, and that is a lookup in the memory from ALU out, which we already have here. Result, but write B to the write port of the memory. So this is the write port of the memory, this is the address port of the memory, this is the read port of the memory. So we need this additional micro operation to perform ALU out. Now what we've done is fully structured the data path to support the required micro operations. We've actually completed the more creative aspects of doing the design and can move on to the controller, which is what we'll do in the next submodule. Before I do that, I just want to summarize. Again, the key steps were, we took our algorithmic intent, in this case the instructions we had to support, and try to work out reasonable sequence of micro operations that are required to support the functionality that is specified by the algorithmic intent. We then roughed out the major hardware blocks that required to support those micro operations. We then try to work out the sequence of micro operations on that hardware in order to get a trial design. We calculated the performance of that design, that is how long it took to perform the instructions, to complete the instructions on average. And what we found that was very long, in this case, because they're a long critical path. So we broke up the critical path, which means changing the micro op sequence in order to try to obtain a design that's more optimal. Once we have the micro ops and the micro op sequence, we can now complete the data path by just inspecting the micro operations and adding features to the data path to support those specific micro operations. And I want to emphasize that, note, we have not yet touched the controller. We've totally focused on the data path. This is the creative element. Get this right and the controller just falls out by turning the engineering handle, and we don't need much creativity in creating the controller. I hope this module was useful to you. Again, the key thing is micro operations and sequences of micro operations are the key step to taking a design intent and starting to turn it into design. Thank you very much for your attention.